explanation of the workshop. As Jacob said, the main organizers are Fundacja Quantum AI and QPoland. I will also tell a bit more about them, but now the most important things about the workshop. So there will be 2 days of classes, today and tomorrow, from 10 a.m. to 2 p.m. both days. I'm the lead organizer on behalf of QPoland and Fundacja Quantum AI, and Jacob is our great instructor. If you have already had the opportunity to see how good he is in conducting these lectures. And we also have two mentors, Tomasz and Sebastian. They're also available here on Zoom and on our Discord. And we'll be happy to answer your questions if you have any. If you have some questions during the workshop, during the lectures of Jacob, feel free to post your questions here on the chat. And after the session, you can also post your questions on the corresponding Discord server channels. You can also post your questions there during the lectures, but Jacob will not be able to see them. But our mentors can also try to help. The graphics were prepared by Aga, our graphic designer. I see that there's still an old link to the GitHub repository, but we've shared the updated link with you by email and on Discord, so you already have it. The lectures are conducted on Zoom. If there are some technical issues, we'll move to Discord, but I hope that we've reached the limit of technical issues for today. Yes, I already explained the main communication. And one important thing is that you can receive a certificate. After solving the final test, we'll share the details later, probably tomorrow after the second session. Yeah, maybe just a few words about the organizers. So the Quantum AI Foundation is a non-profit organization supporting education and research in new technologies, especially AI and quantum computing and intersection of these fields. So we organize meetups, workshops like this one, but also conferences, hackathons, contests. We release newsletters and so on. And QPoland is a member of QWORD. So QWORD is an international network of groups, individuals collaborating, working together globally to prepare educational materials. So the materials that we use for these workshops were prepared by Jacob, but in many other workshops we use QWORD's materials. Yes, so we can follow the social media of QWORD. Just to tell you about the main projects, there are also different educational materials prepared at different levels, starting from the introductory level, like QBronze. There are also intermediate level workshops like QSilver, QNickel. There is a program for online research internships that's called QIntern, and so on. And QPoland is just one of the Q cousins of QWORD. I'm also the coordinator. We have more than 30 Q cousins now in QWORD, and they also collaborate globally, but later organize educational events for the local communities in their countries. So if you are interested in QPoland, especially if you are in Poland, you can also follow our social media and join our Discord and so on. And all the links are on our Discord server of this workshop. So with this, I thank you for the attention, and I will now stop sharing my slides and my screen, and I will give the Zoom back to Jacob.
So welcome to the workshop. I'm Jacob Cebulski. I'm going to walk you through various issues of quantum machine learning. To start with, I'd like to thank QPoland and Quantum AI Foundation for organizing this workshop. It's the third workshop of this type. And each time we have a lot of people willing to join us and explore this area. We assume that you have already done some quantum computing. We're going to use Pendulane, but you may have done it using Qiskit or some other framework. I will give you some small short introduction to Pendulane in the process. So don't worry if you don't know Pendulane. I will also assume that you have some knowledge of machine learning, not very elaborate, but something that you will understand neural networks and the basics. So this workshop will be for people with who may be experts in quantum computing, but maybe not so in machine learning, and opposite would be machine learning experts who want to learn more about quantum computing. If you ever get lost and you don't know how to navigate and where to go, if you go to jacobcebulski.com, that's my website, and if you go to presentations, and there will be an entry point. This is the quantum machine learning workshop, and you have here a pointer to the GitHub and some slides you could download as well from here. And of course, the GitHub, when you click on GitHub, you're going to see this screen. And this is where all the resources are. So please download it. If you know how to use GitHub, you could clone it and keep it updated as we make the updates. Otherwise, you could click on code, download the zip, and unzip it in the place that you could access. And the most important part would be installation guides. And there will be installation guides for Linux, for Mac operating systems, and Windows 11. I'm using Linux, so if you get stuck with the Mac or Windows, we have people to help you. The place you really want to explore is Discord, and we have here the area to get help. So you could get help with lectures. Already someone asked questions. And the meeting chat has been disabled. Okay, so Pavel could help us with that. Okay, so if you have any issues, put questions here. And in Zoom itself, you could ask questions online. At the moment, chat is disabled. So I think that Pavel may need to help us with that. In the meantime, you're welcome to put all your questions in the area here on lectures, on installation, and other things. So most of the practical work will be done after the workshop. However, I will give you some demonstrations, and you're welcome to join me if you have everything installed and it's all working. So today we have 2 sessions, and I'll get into my slides, and I could actually walk you through all the other issues. So let me just display my slides. So this is the first session. The session is taken by me. I'm Jacob Cebulski of Enquantit. I'm Melbourne, Australia. And we were going to cover a number of important topics. What is quantum machine learning? Who is the team that will guide you through this whole learning? What are the aims of this workshop? And then get into the details of what are the parameterized circuits, how you encode data, how you decode the state of the model, how you train the quantum model, how you optimize it, and then look at the nitty-gritty of how this actually happens in Pendolane. So let's dive into it. This is our team. Dr. Pavel Gora, he's coordinator of QPoland, and he's a CEO of Fundacja Quantum AI that is actually helping organize this workshop. Tomek Rybotycki, who is a mentor. He's a QML researcher, and he's part of a variety of different organizations. And Sebastian Zając, assistant professor at SGH Warsaw School of Economics. And he's also participating in some commercial activities in quantum finance. Myself, I'm Jacob Cebulski. I'm the founder of Enquantit. And I'm also holding an honorary associate professorship in quantum computing at Deakin University in Australia. So that's our small team. And we will keep you alive in this whole process for today and tomorrow. So what is quantum machine learning? Because I'm sitting sideways to the camera, I'll just switch the camera off if I can figure out how to do it. Okay. Okay, so quantum machine learning is an intersection of three areas. Of course, it comes from quantum mechanics, but it is enabled by computer science and utilizes a lot of mathematics and statistics that will make it more formal, but also to give foundations for everything we're going to do in this area. If you look at smaller details, it's definitely an intersection between quantum computing, machine learning, and the part of mathematics which drives quantum mechanics, and that's the quantum machine learning. There's a lot of applications already developed in this space, starting with finance and insurance, transport, logistics, aerospace, automotive industry, materials, manufacturing, energy and resource management, chemistry and pharmaceutical. That's a really good fit for applications of quantum machine learning because the phenomena that are described in this area are very easy to simulate using quantum algorithms. And of course, biotechnology, medical, healthcare, and what actually finances a lot of activity in this space is applications in networks and security. So this workshop aims to develop your understanding of this field, but also gaining some skills, practical skills, hands-on in the creation and applications of quantum machine learning models. So there are two objectives for two groups of people who are likely participating in this workshop. So people coming from quantum computing area, you're going to learn about the machine learning, the ML in QML, and of course, people who are already in machine learning, they're going to learn more about the Q in the QML. So I'm going to give topics that will be boring to both groups, and I'm going to cover the topics which will be new for both groups of people. Now, if you look at machine learning, quantum machine learning objectives, there is a lot of models which are being developed. What are the models? Models are descriptions of solutions, the abstract descriptions of solutions. And those descriptors are going to cover different goals. Okay, so we have models such as classification, which assign discrete label to some category. It just puts data into boxes, and the boxes have names. Estimation, they predict continuous numerical value, and this is like predicting profits or predicting the share value of the share on the market. Clustering applications, grouping data in groups, association, discovering rules and relationships between data, dimension reduction, compressing data while retaining its essence, ranking, determining the order of data, perhaps in query answering and getting all the possible answers ranked by the relevance, anomaly detection, finding outliers, identifying abnormal data, synthesis and generation, like creating realistic fake photographs, perhaps. Then transformation mapping, for example, mapping data which is noisy to data which is clean with noise removed. And some action optimization, like learning the policy, maximizing rewards. So there's already a lot of quantum models which fit into those categories, like quantum support vector machines, variation quantum regressors, and quantum neural networks, quantum k-means, quantum clustering, association rule mining, and so on. So there are ready-made models for us. Some of those models are available in large packages such as Qiskit and Pendulane and others. Others are published algorithms which you could find online. We are going to cover only three of those. So we're going to focus on classification and estimation and a little bit on transformation. We're going to look at quantum autoencoders and in particular denoising encoders. That's only the first few steps, but once you um, gain the speed, you'll find that it's easy to pick up more complicated, more sophisticated models as you go. So let's start talking by taking a step back and let's talk about a classical model, the most popular multi-layer perceptron, which is a type of a neural network. Those of you who have already explored machine learning, you know exactly what I'm talking about. It's a network of layers, starting from layers which inputs input data, ending with the layer which will generate output data. And in between, you have hidden layers of neurons or some nodes, which are heavily interconnected, layer between layer and of the neural network. Each of those nodes or neural networks is calculating a weighted sum with some kind of activation function, which basically reduces the calculation of the sum into a specific interval of values, say from -1 to 1, and it acts as a nonlinear transformation of data. What's important is that we could train such a network. That means we could train the weights which are on the links between the nodes. And so when we calculate the activation of each neuron, that activation, it calculates the weighted sum of the activation of neurons from the previous layer. Okay, so by training the weights, we could actually train the network to match the input and output which come from some data set. So that's the mechanics of classical artificial neural network. Now, how does it work? How do we train it? The training involves some kind of optimization of those weights. And some of you may have heard of backpropagation. There could be many other types of optimization techniques for neural networks. But a large class of optimization is based on so-called gradient descent. So what you see on the right-hand side is how it works. Imagine we have only two weights in this very complex neural network, weight 1 and weight 2. And if this network is actually enacted, and for each input it generates some output, we know what is the output that this network should generate from the data set, the training data set. And so we could calculate the error of that particular pair of inputs and outputs, how much it missed in the calculation. And we do it for every single item in the data set. And this is what's called the cost. The cost of the penalty, the error that in total this particular network is at this point, at this set of weights that it produces. And so for each possible value combination of weight 1 and weight 2, because imagine we have only two of those weights, it calculates the cost, which is the elevation of this plane. So every single combination is giving you a point on the weight 1, weight 2 surface, and the elevation is the cost. So if we start at some particular combination of the two weights, we're going to land at this point. This is the cost landscape. So basically, we want to reduce the cost. We want to reduce the error this network is going to generate. So we want to find a point on the plane somewhere at the very bottom where the cost is the lowest. So we need to find perhaps what we could do is to calculate all possible combination of two weights and then find the minimum. But if you consider that the network may have thousands of those weights, this space would be 1,000-dimensional. And so it would be impractical to calculate all possible combinations of weights and weight values for given network. So the optimizer is actually more clever than that. The optimizer is looking at the hill down the cost landscape towards the minimum. So it does some calculations near the point at which you're standing and takes the step down towards the lowest point. It can also do some additional hops left and right in case we have some little holes and little potholes on the way downhill, so we could jump out of those potholes and continue moving down. So this is basically how gradient descent works, and different optimizers will have special features, how to quickest find the path down towards the lowest possible point in the cost landscape. So gradient, in case you're not familiar with the term, if you look at this cost landscape, the shape, which is geometry of the cost landscape, is basically the angle pointing down. And of course, the angle pointing to horizontally, gradient is 0. This is the point we're looking for. So that's basically how gradient descent works. Now, the optimizer may be controlled by some hyperparameters. That means the parameters which describes its behavior. And there's one of them is called learning rate, which indicates how long are the steps that the gradient descent takes. The momentum, which is basically looking at the acceleration of moving down. So it takes the previous step and the direction of the step, and continuation is going to be point in that same direction a little bit. Decay is basically as we get closer and closer to the bottom, the steps should be smaller and smaller. So decay is shrinking the steps in this process. And epsilon is basically your tolerance you're going to accept as being satisfied to reach the minimum. So epsilon describes basically how far from the very minimum you'll be happy to use as your best point, the optimum. Okay, so in my little example, I had data about housing, and I accepted two different variables only, lot frontage and intercept as values A and B. And based on those values, I calculated on a very simple network, the error, the minimum error was 53,000, mean absolute error. Okay. Now, what happens with quantum stuff? Okay, in quantum world, obviously things must be different. So you're familiar already with the notion of a circuit. And the circuit, quantum circuit, is basically the representation of an algorithm which spans a number of qubits available on a given machine. And the circuit defines the operations which are being performed on the state of individual qubits. And there could be like rotation operations, or could be also operations which interrelate multiple qubits. For example, there could be entangling operations between two qubits. So normally the circuit would start from encoding of input at the very beginning. Then there would be layers and layers of rotation blocks, entangling blocks, and eventually some measurement. There could be a measurement of a single qubit or more than one qubit. And that measurement will give you some value, and we need to interpret those values to find out what are the actual real values this network is computing. And of course, the input also needs to be transformed so that it could be accepted by the network. For example, in this particular case, we used rotational embedding of data. That means the angle of the state rotation in a given axis, whether X, Y, or Z, is going to determine what is the value encoded in this process. And of course, the values have to be limited because you could rotate only from 0 to 2 pi of rotational angle. So that's a typical circuit. The problem with the circuit is that it doesn't look very much like the neural network where we could train the weights, because all the weights, which means those rotational blocks which we have operations, all these weights have been hard-coded into the circuit. So a circuit gives you a rigid structure which is suitable for execution on a quantum machine, but it's not good for optimization and changing parameters. So what we need to do is to create a template which is overlaid over this rigid static circuit, quantum circuit. And that template is going to define parameters over those operations. And so what's going to happen if we want to optimize the circuit? It has to involve 2 processes. One process will be running on a classical machine, and another process will be running on a quantum machine. On the classical machine, we're going to use the parameters, optimize those parameter values, the same way we do it in a classical neural network. But once we instantiate those values at a given training iterations, we get a fixed circuit which could be submitted for evaluation to the quantum machine. We could get measurement results, get the measurements, and feed it back to the optimization algorithm to determine what should be the next set of parameter values, weights of this circuit. Also, the same happens with inputs. The inputs are encoded as operations with specific angles, which means specific values are being encoded. So the inputs need to change as well. So each instantiation of inputs and weights is going to give us one particular instantiation of the circuit, and is good only for a single run. And each time we need to run it multiple times to average the results, because each time we have a bit of fuzziness and uncertainty as to on each operation. So this is basically what variation quantum models look like, and the algorithm which is animating this and discovering, optimizing the circuit is called the variational quantum algorithm, VQA and VQMs. The circuit, the parameterized quantum circuit, it's actually the name for the template which we were talking about. Okay, so far so good. Everybody's happy with the concept of circuits. I don't know if you are able to send messages now. Okay, excellent. All right, so now the question is, what are the options in terms of how do we encode data in quantum circuits? And the second question is, how do we read the output out? Because they are very different to what happens with normal algorithms. Now, you're familiar with quantum algorithms and circuits because you've done it in your previous life. So this is just a reminder. We have many different ways of encoding data into circuits. So the 2 most basic ones are the basis encoding and angle encoding. The basis encoding, basically you use qubits and set them to values 0 and 1. So initial qubit may be initialized as 0 state. If you use the X operator, it will turn into 1 state. And so basically, you could encode a single value across the whole circuit. A single value because this is like bits of a number encoded directly engraved into the circuit. So it's simple, it's solid. You can use it if you want to feed data, which is a single value at a time. What if you wanted to have multiple values encoded in a circuit? Multiple values can be encoded by rotational operations. That means each qubit could represent rotation, a single number, if you use a single rotation like Ry, or you could use two numbers at the same time. So you could say perhaps Rx and Ry could be encoding of some value. So a single qubit could encode perhaps two possible numbers. There could be other algorithms. There could be the amplitude encoding, QRAM encoding, which could saturate the circuit with multiple values. You could represent exponential number of values to a number of qubits. But there's a penalty for that. One of those penalties and the difficulties is that each set of numbers encoded will generate a different structure of the circuit. And that is a bit of a problem for the optimization of execution on GPUs or quantum machines. So that is great because amplitude encoding is encoding the data in the same way you read it out. However, we have some technical difficulties in terms of using such circuits. So in this workshop, I'm going to focus on angle encoding, and the simplest, very flexible, and however, what you encode depends on your intention. So perhaps if you have just positive numbers, let's say from 0 to 2 pi, this is the range of your encoding. Or you could have encoding from minus pi to plus pi, or you could encode it in relation to some state, like the the ket state. Up would be negative numbers, down could be positive numbers. We have a lot of possibilities. We're going to use the simplest. We're going to use rotation to the left as negative numbers, rotation to the right as positive numbers. So this is the angle encoding, and how you measure it back of what you encoded, that's a little bit of a problem. We need to figure out how to decode rotation from the measurement, and the measurement could be given in terms of either expected values, as in here, so from -1 to 1, or could be as probabilities of different outcomes. So, but we'll worry about that next. On the right-hand side, we have different ways of measuring the state of the circuit, and not only measurement, but also interpreting the outcome of the measurement. Okay, so what are the choices? We could measure a single qubit at the end, so hoping that in the training, all the meaningful information is going to be channeled into the state of a single qubit. Okay, that's called local cost measurement, because that measurement eventually is going to translate into cost, the elevation of the error plane. Or we could measure all qubits and interpret it in some way. It's called global cost. And whether you interpret single or multiple qubits, that will have an impact on the complexity of the measurements and interpretation. But we have those choices. We can also split qubits into groups and interpret them as multiple, representing multiple variables. Now, when we talk about circuits which may have potentially thousands or hundreds of qubits, that's actually an interesting proposition, because in such cases, we need to be clever about measurement, in which case global cost measurements may be completely unacceptable. You can't possibly measure all qubits at the same time. And so you need to sampling of qubits for measurement and interpret it in different ways. Okay, I'll talk about data reuploading that Tomasz mentioned, and that will be coming soon. Okay, so we have here choices in measurement, and keep it in mind that the modern quantum machines are moving to very large circuits, in which case what we are talking about here needs to be modified and need to be adapted for developing those large models. Okay, if we measure a single qubit, and let's say we measure probability of 0 and 1 on the single qubit. If we repeat the measurement multiple times, we're going to have certain number of outcomes will be given as 0, certain number of outcomes will be 1, and so you sample the data from the qubit, and this already has some representation, which could be interpreted as perhaps a logical value. The higher the frequency of zeros will give you perhaps a false as a result, or 1 if it was 1 with the higher bar. So that's very simple, logical. But at the same time, we could interpret, let's say, the measurement of 0, the height of the bar, as the floating point number between 0 and 1. So probability on a single qubit can be interpreted as a number. If we repeat it as in global cost measurement, and we have possible outcomes of all qubit values, that's actually very interesting because we have a lot of flexibility here. For example, we could interpret the height of the bar as the tallest bar as a floating point number, but we could also look at the combination of possible outcomes of different qubits as an integer value. Okay, so we could interpret the measurement results already as a logical value, as an integer value, in different way, or sorry, floating point value, as the height of the bar or integer. And we could also possibly could be interested in the whole probability distribution and interpret it as a multiple value outcome, which of use to some computation. Okay, so we're going to be looking at all those options in our workshops, in examples, and you'll see how we could actually play with the interpretation of results to get some meaningful insight into the computational outcome. Now, when we're going to use angle encoding, we have the good, the bad, and the ugly. Okay, it's to do with the scope of possible values which could be encoded in that way. So imagine that we're going to have possible encoding of values to the right in blue, the positive values, to the left in red, the possible values, negative values. If we were going to encode values between -6 to 6, so what's going to happen is that -6 actually is about pi, it's just a little bit below 2 pi. Negative, the same blue, the +6 starts at 0. We're going past the pi value. We continue and we end up close to the other way. What it means is that there's a potential conflict between encoding positive values and negative values. They will be overlapping in this representation. So the value somewhere here would be maybe 3, this will be 2 pi, so it's 1.5 pi positive and minus pi negative. So this value will be in conflict. And basically, if you are going to create already errors at the encoding, there's no way you could get meaningful outcome later on. It's a disaster. So basically, you need to rescale your values so that perhaps they encode it in different ways. Imagine we're going to rescale it from minus pi half to plus pi half. Okay, so we have a full pi. And in this case, there's no overlap of those values direct. But if we're going to measure this representation of those values onto z-axis, projective measurement z-axis, then we're going to have instantly the conflict in interpretation of those values. So the values themselves were not in conflict, but the measurement of those results will be in conflict. That may or may not be correctable. If we start rotating the qubit in x, y, and z axis, most likely that would self-correct itself. Okay, but this could be a problem. The problem that we start with the potential conflict in the interpretation of the state. There's another possibility. Let's say if we wanted to represent the values of sine x by representing x directly. So we start with x from 0 to pi. Each value is unique, but it could be that the sine x, which is supposed to represent, will be in conflict on two different possible values of x. Okay, so in here, I'm not representing sine x directly, but by different encoding scheme, which is actually looking at the value of x itself, which is silly here. So basically, if you use angle encoding, you have to keep it in mind that you need to avoid conflict at the very beginning of encoding the data. Because if you create errors at start, there's nothing you can do about it later on. Okay, so keep it in mind. The two principles: distinct data values should map onto distinct angles and distinct amplitudes, ideally at the very beginning. And the same data values should always map into identical angles and amplitudes, as would be the conflict in the middle. Okay, so keep it in mind because you're going to see it in our workshop. So again, looking at the structure of the circuit, and we identify three components: the feature map, responsible for encoding the data; the measurement block, responsible for measuring the result; and in the middle, what we call ansatz, which is a parameterized circuit with trainable parameters, which would be weights and biases if we want to refer back to the artificial neural network, the classical neural network. If we're going to train it, we have a lot of options. The feature map could have a variety of structures and functions. Okay, so we use the simplest one. The ansatz could vary in the width, number of qubits, the depth, number of layers, the number of parameters, which is representing, like here, each operations is having three different parameters, rotation around, I think it's about Z, Y, and Z axis in that sequence, or you could think about X, Y, and Z axis rotations. The structure, you could have a flat structure like in here, or you could be funneling it in and out. And then the way entanglements are structured, you could, here we have the circular structure of entanglement, you have linear entanglements, you could have rotational, as changing, you can see the first rotation, the next entanglement, and they vary at each block. And so we have this flexibility, which is great. So we have lots of options. The ansatz layers consist normally of rotational blocks and entangling blocks, which is R or U, X, Y, Z rotation, and the CNOT gates for the entanglement. And if we were going to train it using classical optimizers, we have choices. A lot of quantum packages, such as Qiskit and Pendylane, they already come with their own optimizers. But you could use something like PyTorch, which is what we're going to do in this workshop, in which case you could borrow a much richer spectrum of optimization techniques available to those machine learning packages. So we could use gradient-based optimizers like ADAM, NADAM, SPSA. You could use linear approximation methods. Cobula, those of you who work with Qiskit, you know that Cobula is fantastic optimization workhorse. We could have nonlinear approximation methods like BFGS, quantum natural gradient optimizers. That's the only optimizer which understands what happens actually underneath the cost landscape, what happens in the quantum space. And then we could use different cost functions, R squared, mean absolute error, mean square error, Huber, Poisson, cross entropy, hinge embedding, Kullback-Leibniz divergence, many more. And the circuit could be executed not only on a real quantum machine, not only on your laptop, on CPUs, but also on accelerators like GPUs and TPUs. Now, in all of this, we need to be aware, number one, that if we add a single qubit in the structure, we add first of all, more possible states that this circuit represent. It doubles number of states which can be represented in a Hilbert space, but also we add more operations and more entangling CNOT operations. So your complexity of the structure grows exponentially. Also, we need to be aware that adding a single measurement doubles the number of outcomes. So if we look at the probabilistic results, we add an extra bit because each qubit is interpreted in its state. And so suddenly we have double number of possible outcomes. And so that could be a problem in terms of interpreting the results. We lose the resolution of the results. So keep those in mind. Ideally, we like to keep them small and easy to manipulate. Okay, I mentioned Hilbert space, and you should be already familiar with the Hilbert space. And those of you who've done a proper quantum computing course, you would have seen this notation, the bracket notation. And I'm not going to walk you through this, but you could definitely, I invite you to study this slide. What I want to show is that as the circuit executes, the state of the circuit evolves. And so it evolves from the simple initialization of 2 qubits in this case. So this is a simple ZZ feature map, which is available in Qiskit, for example. And each operation is applied, the state evolves. So it evolves from, in this case, I show you layer by layer how the state changes and eventually reaches the very end, which can be measured. And the final state of this particular simple circuit, layer by layer, it actually grows and shrinks because we are suddenly getting states which cannot be expressed as by a single qubit, but only as a combination of qubit outcomes. So in this case, the result of those 2 qubits will give you a complex state which is mapping onto combination of possible outcomes of qubit 0 and qubit 1. Okay, so what's important in this is that that state is represented in a Hilbert space. The Hilbert space is spanning the exponentially number of dimensions as there was the qubits. And even if those qubits get entangled, we have subspace, which shrinking in dimensions, but is still embedded in this exponentially large Hilbert space. Now, each state is represented by the state vector, like what you see on the top, which is the very final state. And as the circuit executes, we're moving the state of the circuit from one point, from one vector to another vector to another vector. And you can imagine that in this multidimensional space, we are plotting a line, which is the line describing the changes of the state of the circuit. And of course, because we deal with quantum phenomena, each time we run the same circuit, we get a slightly different line. Each time we decide to use different parameters in the circuit, like the input data or the weights, that line changes, it drifts away as well. So if we look at all possible data sets, all possible parameters, we can draft a very complex surface, multidimensional surface in Hilbert space, which describes the geometry of this circuit. And that actually is very interesting to study this geometry because some of those geometries will enable you to optimize the circuit, and some of those geometries will be acting against it. Okay, so keep it in mind that this is what happens when the circuit is executing, and you could actually theoretically predict what is the shape of the geometry, which the surface of the circuit in the Hilbert space. Okay, that's actually shown slightly here. Okay, imagine that we used imagine that we use a circuit, which is here. The state of the circuit execution are represented in a Hilbert space. And of course, there is a classical optimizer that it could see is only the parameters of the circuit, and actually maybe not even the parameters, because you can't actually look into the circuit during execution. You can only see the final outcome, the cost that this circuit generates, given some input and output, and maybe the whole data set on the input and data set on output. So each point on this classical parameter space is actually showing the path of the optimization to find the best optimal set of parameters, which the optimizer maintains independently of the quantum circuit in its execution. Okay, so classical optimizer is completely oblivious to what happens in Hilbert space. It doesn't know that the circuit has entanglements, which means the parameters which it's planning to inject into the circuit, they are interrelated. So if you change one parameter on one qubit, let's say operations, rotational operations, because of entanglement existing between the qubits, automatically the other parameter changes as well. So those are so-called non-local interactions, which the classical optimizer has no idea about completely. But it's doing some work, and the work is much harder than using having a classical optimization. Okay, so keep it in mind. Optimizer, I call it, it's a blind puppeteer. It's just looking at its own surface, has strings attached, but it cannot see the puppet dancing below in the Hilbert space. It can only hear the audience cheering or enjoying the show or not enjoying the show. It doesn't know what's happening. It can only see the final outcome of measurement, and that outcome measurement is going to plot the path towards the optimum area of the optimum parameter sets that this circuit will be optimized for. So that's actually, keep it in mind, the classical optimizers have no knowledge of the complexity happening in Hilbert space. They don't know how the evolution of the state is changing step by step, and is still doing the work. Okay, there are some special optimizers which could predict the behavior of the circuit and its state in Hilbert space. And I mentioned that here before. This is the quantum natural gradient optimizer, which understands that we are actually operating in Hilbert space remotely via the optimization. Okay, we're going to go into Pendylane, and we're getting just in time, I hope. So Pendylane, some of you are already familiar with Pendylane, and some of you may have experience with Qiskit. The first important thing is that Pendylane, it's actually embraced differentiable programming paradigm, and is very different from Qiskit. Pendylane is purely functional. Everything is functional. And the reason for that is that it was developed by Xanadu, and Xanadu specializes in photonic machines in which the circuits have no physical representation as they are with IBM circuits. So basically is the state of light interference which creates the state, and the circuit is sort of stitched by light into space and disappearing. Okay, like function executing, and the functions as they combine, the values change, and eventually, as a side effect, you have a result. That's how Pendylane works. And this will be very critical to shift your mind from programming in Qiskit to programming in Pendylane. It integrates seamlessly with Python, has a range of operations for state preparation, gates, and measurements. Uh, on From the point of view of understanding the circuit, is like any circuit in any other gate-based quantum machine. It has lots of quantum algorithms which can be developed. It executes on simulators and quantum hardware, including hardware which doesn't belong to, from back end, could be actually IBM quantum machine, has error mitigation, and it's extended with a variety of different other packages, which provide different ways of calculating gradients, which help you navigate the cost landscape from JAX, PyTorch, Keras, TensorFlow, and NumPy. And definitely is very good for combining classical components with quantum components, as long as they can be expressed as differentiable functions. So Pendelane is fantastic for putting together a matrix with a quantum circuit and with classical function together in a single solution, and optimize all of them in exactly the same way. Okay, so it has a lot of quantum models, maybe not as extensive as in Qiskit, with quantum neural networks, quantum kernels, Fourier models, and definitely can be extended with PyTorch. I think that TensorFlow may be dropping out with time, but at the moment, I think there's support for TensorFlow. So what we're going to do, we're going to start with very simple demonstration and then move into more complex, and hopefully we're going to finish it in half an hour, all of it. It sounds like impossible. However, you're going to see that the way we're going to work is going to be as follows. So if you look at the structure of the repository, most of the examples will be in notebooks here. There's one example which relies on data, which in the past we used to fetch it dynamically, programmatically, but it looks like the university repository disappeared, maybe got blown off the space. Maybe it was in the Gulf somewhere. Installation instructions I mentioned. Lecture slides are here in slides. And each notebook is structured. Okay, so we have session 0, which you're going to explore on your own, but I'm going to walk you through some of them. Session 1, session 2, session 3, and 4. Okay, so we're going to download it, and once you download it, you're going to have the following. So all session 1, session 2, and 3 start with a detailed description of what you're expected to do, what data you will manipulate, what are the tasks expected of you to do. Some of those tasks I'm going to show you here. Some of them you're going to continue in your infinite free time at home. Maybe at the end of the day, today, instead of going to bed, you're going to hack the code, the Pendelane code. Okay, so in session 1, I'll give you a lot of help identifying where the changes should be entered, like task 1, follow the instructor demonstration. Task 2, somewhere it will be here. I may have missed it. Okay, so I indicate where the changes would happen, but in the future sessions, we're not going to do that. Okay, so I'm going to walk you through first the very simple, much simpler Pendelane basics. Okay, so this is a tiny model to explain the principles of quantum machine learning using Pendelane. I'm going to walk you quite quickly. Okay, so first, there is actually the utilities functions to simplify some of the actions that we're going to do. So for plotting and for drawing the circuits, so they look like Qiskit circuits. So first I need to show where I'm looking for those utilities. I'm going to use matplotlib, obviously. I'm going to use those utility functions. And here is the most important one. I'm importing Pendelane as QML. I think that nowadays they want to give a different acronym than QML. This is important. Pendelane is going to redefine the NumPy. Okay, so I define NP, which is NumPy from Pendelane. What's the reason here is basically it allows Pendelane to use a variety of different gradient styles, not only the one which is based in NumPy, but also JAX and many, many others. So it redefines NumPy. You get all the standard functions from NumPy available to you. I'm going to import some optimizer, and I'm going to import Torch. Torch, the neural network. I'm not going to use it here, I think, but just to show you that I'm going to import things from Torch. You'll see that in a lot of my notebooks, I'm importing Torch, even though I'm not using it. The reason for that is that Pendelane internally uses some Torch functions. And if you work on Linux, unless you import it physically into this notebook, Pendelane may look at around, says, is the Torch around? Not in memory, therefore I will make your computer work very slow. Okay, so that happens for Linux machines only. If you work Windows or Mac, I don't know if Mac is the same case, but I think Linux is the problem. So let's import it. Okay, first of all, I'm going to say what type of qubit I'm going to use. And basically, it allows us to execute this code on a variety of different platforms. Perhaps in CPU, but perhaps the GPU, NVIDIA GPU, some other GPUs, maybe IBM machine. And so each one will be using different qubits. If you're going to install Pendelane according to our recommendation, you would have installed default qubit automatically. It comes with Pendelane package. And there's a Lightning version of Pendelane. It's written in C++. It gives you very fast qubits. So here, basically, default qubit is the safest, but maybe slow. I'm going to create some test data and weights. And the first thing you're going to see, I'm using NumPy array. And I'm going to specify that data on input does not require any gradients, but weights of the quantum model, they require gradients. That's because the weights will be manipulated, and we're going to look for the optimum point in the cost landscape. So we need gradients. We need to be able to allow the optimizer to seek the bottom of the cost landscape. And you can see that this is no longer an array, it's a tensor. And in case you wonder what's a tensor, you could think already tensor is it's not an array of data. Tensor, it is some representation of some geometry, multidimensional geometry in space, which has directions. So you could actually attach directions to every data point in this space. So this is a tensor. This tensor requires no gradients. So this is like normal weights, but this one has gradients. And we could actually find what the gradients look like. Okay, this is the first simplest circuit we're going to build. We specify first that what device we're going to use, which means what is the qubit we're going to use, how many wires or qubits we're going to have, 2, and if it executes, how many times it will be repeated, the measurement will be repeated, 1,000 times. Okay, so here's the circuit. This is the adornment, which indicates that this function is not just a normal function, but it is the function attached to this device. So it means that it is a function, as you can see, it takes inputs, manipulates inputs, produces results, but it will be executing on a specific device. It could be GPU, it could be memory. And inside, we have references to QML, which is PenDelane, and we're building gates. We're building gates and attaching them to different qubits, qubit 0, qubit 1. We specify what the values are going to be present there, inputs, and also weights, what weights and what qubits, exactly as you would do it in Qiskit if Qiskit is the language of your preference. At the end, we return the measurement, and the measurement in different ways. So here we're going to return as probability distribution of different outcomes. And how do we draw it? Okay, the first thing, maybe we should have actually run the circuit as a function which takes input and output and waits, just to show you that you could execute it right away. Okay, so we got probability distribution as probability of outcomes 0, 0, 0, 1, 1, 0, 1, 1. So that function actually ran a quantum circuit. It's a function, but it's attached to the device. It is actually a circuit constructed as a side effect of running this function. And just to show you that everything's functional, if I want to run the circuit, first of all, I cannot actually show you the circuit unless I run it. So there's no static representation of the circuit. The circuits exist only in space as it executes. Okay, so I specify I'm going to have a function circuit. That function will be put in a wrapper which allows you to draw it and then pass values so that the circuit could be constructed functionally. And this is what it looks like. Okay, so here we have a circuit representation. And I showed you that before. Have a look. We have a slightly different outcome. That's because we're dealing with quantum effect. And so the values will not be identical each time. But if we run it multiple times, we can plot the histogram of probability distribution of that single or multiple results. We can also explore the gradients of the circuit, and the gradients are returned as a Jacobian matrix, which is partial differential values, which is showing the probability outcomes of measuring state of ij, probability 0, 0, 0, 1, in respect of specific weight, the trainable parameter. Okay, we can look at it later in the process. And we could actually access those gradients. Again, those gradients are accessible only when the circuit is executing. At any given point in time, I can find the gradients attached to the weights. And the weights, the values of the weights have to be known. And again, we run it a few times. Each time we have a different result. Now, what's going to happen if we pass the whole lot of values to the circuit? Okay, so here I put input 5 times. I created a stack of those inputs, and I want to pass it into the circuit. I expect 5 results from this. Each result will be 4 values. And I don't. What's happening? What's happening is that the function works as follows. It says, whatever input you give it to me, the first element on input should be put on wire 0, the second element on wire 1. What's the first element? The first element is this. I have 2 values. Because I give it 2 values, but only 1 is expected, so value 219 is put on wire 0, and the second is put on value on wire 1, and everything else is ignored. So clearly it's not doing what we expect it to do. And so that means we need to create the circuit in a different way. Why in the circuit? I just made a circuit, random circuit, just to illustrate the point here, okay? Okay. Okay, so I create a different way of dealing with data in PenLane. Okay, the first is that the way the circuits are going to execute, the circuit is compiled and is transformed into a sequence of operations that will be performed by quantum machine or the simulator. Makes sense. And the way the data is attached to the variables there is that the data is attached to a stack of values. So we could create a batch circuit in which we attach not a single value like input 0, but we could attach the whole slice of values, which is on 0 element. And then the whole slice of values on the first element of each value on the input. And the same with weights, in exactly the same weight. So what it means is that that stack of values we passed through the compiled version of it, and then executed one after another. It will look exactly the same from the point of view of picture of what the circuit looks like, but it will execute differently. So now we can see that we have 5 different outcomes because now we attach the stack of values on input 0 in the circuit to gate Ry, and a stack of other values to another Ry. The same with weights. And so when we execute it, we get multiple results produced. If this is too complicated, you can always run it in a loop and pass just a single value at a time, which is fine, but it's much, much slower. Okay, so now the same circuit could be measured differently. Instead of returning the value, which is probability distribution, we're going to give expectation value. So if we give a single value input and output, looks the same, it's very confusing, is the logic which changed. If we run it, we get only 2 values coming out because this expectation value from -1 to 1 is basically probabilistic distribution of those values on the measurement. And this is a very different representation of results. So expectation values, they give you single value on the measurement of each qubit individually. Now, probabilistic distribution, we have distribution of different outcomes of all possible combination of outcomes on the result. And again, we could create a batch version of the circuit. And because probabilistic distribution is a single outcome, but multiple values, it looked right straight away. In this case, we expected 5 possible outcomes. We only showed 2. That's because we need to invert it and have a proper outcome. So here we have multiple outcomes coming out. Each outcome creates its own series of results on measurements, because that's how we want to measure. We want to measure each qubit individually, and those measurements are returned. Okay, what we need to do next is to show some real example. And this real example is going to be your nightmare, hopefully. So what we're going to do, we have a simple function, sine function, and a more complex function, sine 0.7x plus 0.5 pi. Okay, we start with the first one. And what we're going to do, we're going to have a number of tasks. The first task will be, I'm going to walk you through this, and all the other tasks you'll try to do yourself. And you're going to hate me by giving you alternative data, because no matter what you're going to do, you're going to cry. Okay, so the first task will be just to run the code as it is. The second will be trying to improve the results. Okay, trying to change initial values for reduce high values for training. You can try to improve the model by changing the ansatz structure, using more qubits, fewer qubits, more layers, fewer layers, changing data encoding, gauge from RY to RX to see what happens. Try to run it with a single qubit and we see what happens. Okay, so with a number of different tasks for you, and then use a different data set and see if you get the same results. Again, I'm here importing Pendulane. Importantly, Pendulane import NumPy as NP and import Torch. Okay, I'm going to walk you first with what you see. I'm going to use a sample of 64 data points. I'm going to create the data. I use 2 qubits in 4 layers and train it in 50 epochs. And I use some random seeds so that you could have the same result as me. Let's prepare the data. So I'm going to use X and Y. And this is what the data looks like. It goes from -6 to +6. So that could ring the bell from -6 to +6. Is it going to be a problem or not? Now, we could use a default qubit. We could use a Lightning qubit. Lightning qubits will be fast if you installed that library. I'm going to use Lightning qubit here. And I'm going to construct 3 models. A very simple model, which I'm going to run here. The second model is more complex. And the third model, more complex. Those models are using re-uploading of data. That means the data will appear many times in the circuit. So that's interesting because we thought the feature map is at the very beginning of the circuit. It doesn't have to be. The data can be encoded in many, many places across the circuit. Why would we do that? It's sort of like the circuit is going to be evolving and optimizing, and sort of like halfway through, it's a reminder. Remember, this is the data we're working with. And that same data could be repeated on the same qubit, on different qubits. So it's sort of like creating an equation, a function, which has x appearing many times, maybe once x to the power of 1, x to the power of 2, 3, and 5. And the further into the depth of the circuit, you could imagine that those x's are raised to the next power in this function. Now, what is the structure of the simplest one? We're going to simply encode the data with the rotation y on the wire 0. And then we're going to create the basic entangler layer. It's a standard function in Pendulane, which will build the structure of parameters and entanglements. And then I get expectation value on qubit 0. So specify I'm using the first model. It's like attaching the function. I'm going to build the cost function. Okay, I'll come back to that maybe later. But what's important is that the cost function must be differentiable. That means every single point of the cost function must be smooth. So we're going to use mean square error because mean square error is differentiable cost function at every single point. Mean absolute error is not, because at 0 you have the angle. It's a non-differentiable point. So mean absolute error is not a good cost function or loss function for Pendulane. I'm writing my own cost function because if I use standard cost function borrowed from another package, that may not be differentiable, and it's actually not visible to Pendulane. Okay, so I'm writing my own cost function here. that will be clear later. So I'm going now to build the model. I'm going to build the data for the model. So first of all, I'm going to get some test parameters. So how many parameters we need to build, or weights? It depends on the shape of the data in this model. Okay, so we have here a lot of weights, parameters. We depend on how many qubits we're going to have, which is number of qubits. And how many layers we're going to use. So let's look at it. So build the model using test parameters and some data. The data was created before. I'm going to show you what is the test parameters here. We can see here that we have, and what's the data? The data will be many points. We have a lot of points on data. And the weights are going to be indicating how many layers we're going to have. Let's look at the structure of the circuit to understand what's going to happen here. So this is the standard way of drawing the circuit. And this is using the more beautiful structure. And I have actually written the helping function utilities to do this automatically for you. So what happens here is that I requested that I'm going to have the circuit of 1, 2, 3, 4 layers, one input. So 4 layers, each layer has weights as rotations. So each layer has 2 weights, 2 weights, 2 weights, 2 weights. That's reflected in the structure of the parameters. So in Pendolane, the way you pass in the parameters is to match the structure of the circuit. If the circuit has layers, the parameters, the weights must also have layers. Okay, that's why we need to be able to figure out what is the shape of the weights inside the circuit. When we actually build it later on, it will be more obvious. I'm just at the moment throwing a lot of concepts at you. So now we're going to initialize the model. So I create again. So this was actually for testing it. So I use some test data, test weights, test parameters. Now let's actually do the real thing. I'm going to use an optimizer, classical optimizer, Adam optimizer, using some step size 0.5. We could play with that. We're going to build initial parameters which are good for this particular circuit and structure, which I showed you a moment ago. And here's the training loop. The training loop is very simple. I'm going to collect the cost for plotting. I could be collecting the parameters as well. And so I'm going to get initial parameters transferred into parameters will be changed all the time, layer by layer. I'm going to record the time. And I'm going to do it a number of epochs, a number of iterations. So each time the network or the circuit, the model is going to learn a little bit and adjust the weights to reduce the error. So we're going to use a function, which is a function of the optimizer, step and cost. Okay, it's a standard function which takes the cost function. The cost function takes only one argument, the parameter. So that cost function is not quite what we want. So I'm creating a lambda function in which the lambda function understands that I should get x and y coordinates and the model, which was defined above. And then the parameters is a second argument, will be fed into cost function repeatedly at each step of the iterations by step and cost. So what step and cost does? Those of you who are familiar with Torch, you know the basically the steps are as follows. You first do the forward step. That means the forward step is going to put the data through the network and calculate the result. Then the cost is going to be calculated, the error the network makes. And then given the error, we do backwards cost, we do forward and now backwards, we propagate the error and we change the parameter values. So the result of that is the calculated cost and the parameters used to calculate the cost. The new parameters are going to be defined here. Sorry, so this is actually the new parameter sets. This is the cost before the parameters changed. So we keep track of the cost. That cost is returned to us as a tensor. And so to be able to get the value out of it, I specify get the item from the tensor and do it and run it. Okay, because I'm using the Lightning qubit, is very, very fast. We'll plot the results. And we'll see how well it matched the values. So predictions were pretty much good against the original. And we can improve it. Actually, we started with about 20, but 50 is very good. We could actually get much, much better outcome by playing with this result. So this is the first approach to Penny And in your free time, I ask you to take it on board, try to manipulate the structure by giving it different layers. So I'll give you one example. Let me just change it very quickly. As I'm going to change the number of qubits to 1. Would it give better or worse results? I don't know. Where is it? Here. Yeah, at the very top. Number of qubits, 1. Number of layers, 1. And I'm going to run all of it from top to bottom. So let's restart the kernel and run all cells. And perhaps it gave us better or worse result. It's amazing thing is that we get actually a better, maybe not better, almost as good result as before, even though the structure of the circuit is like this. And I wonder if you could figure out why this circuit, this minimalist circuit, is giving us good results in spite of everything. Why we don't need to have a very elaborate model with many, many parameters to fit the function. There must be some good reason for that. Anybody? The feature map. Well, the feature map is this one. And this is one parameter. But indeed, the function, yeah, so actually we're learning the sine function, and this actually emulates the sine function directly. So this may actually shift it slightly. If we want to learn cosine, it will shift it slightly. But I said that means we are learning the function which this circuit emulates naturally without doing anything. Okay, so the real challenge would be if we change the data and see if by doing that, if we comment this out and we comment this in, would it still work? Because you can see here, the fit was almost perfect. Now let's rerun it and see the result. And we're going to have a break any minute. You can see here, I have the same number of iterations. The cost is the same all the time. That means this network is not learning anything, very little. And this is the fit. Okay, so um, that is a huge challenge exercise for you. How can we improve it to fit it better? Okay. And the answer is actually, well, could it be a barren? I'll talk about barren plateaus next. It's a good question here. It says perhaps 2-qubit circuit would work better. Yeah, let's put it in. Maybe 2 more layers, 4 more epochs, maybe. Two qubits with 60. Well, I put it 100. Okay, so 2 qubits, more layers. It's learning something, but it's not fitting yet. So welcome back. Again, I will briefly show my face. Hello, those people who come late. I'm Jacob Cebulski, your instructor. We had a session 1, which was packed with things. And if you felt you were overwhelmed, you should be. And you'll see that the next sessions will be easier. That's because we're going to focus on higher level concepts in PendelLane and a lot of intricacies such as gradients and the way optimization works can be simplified. This session is going to be focused more on people who are lacking machine learning principles. But when it comes to the example, I'm going to walk you through slowly through model building and model optimization. We'll have more time to do that. Okay, I'm going to switch my camera off because I'm going to sit sideways to the camera. Okay, so hopefully you can see this slide. Quantum machine learning, we're going to focus on quantum estimators. And I'm going to walk you through the entire QML process, talk about estimation, linear models, the way we prepare data and partition data, create the model and its training, and then looking at making the model better, scoring the model. So also I'm going to mention the issue of barren plateaus. Someone asked, are you going to talk about barren plateaus? Yes, I will. And I will explain how those problems arise in training. Okay, so let's get into it. First of all, this is just a high-level concept. A lot of us talk about quantum model development as if it was something special, as it was something which is what researchers do. It's not quite, because eventually you want the quantum model to be part of a larger analytic infrastructure. It has to find its niche in data analysis and has to interact with many other components in organizational systems. So we usually start with some research question because that's where this is currently the domain of quantum development. Some difficult problem, very complex problems which can only be solved using classical methods. So we need to define the business problem. We need to define the scope of what we're going to do and how it's going to fit with the remaining parts of systems. Now, the beauty of environments such as PendelLane is that it's very easy to integrate your quantum solution with other parts, classical components of a complex analytical computation. We're going to represent data and fix the data, understand the problems, and you're going to see that the data we're going to deal with next has problems, and we need to resolve those problems. We need to understand the data, repair the data, identify relationships existing in the data, and eventually develop and apply analytic models. Here I talk about analytic models, not necessarily quantum models, because you're going to be developing classical models and quantum models. Often you're going to develop in parallel the same solution in classical and quantum wise. And in a lot of cases, you'll find that the classical solutions are going to beat your quantum solutions, unless you select your problem very, very carefully. It's quite a challenge to evaluate those models and compare them, and then determine which of those models is to be used and how to optimize it. And especially when you compare quantum models to classical models, you read probably a lot of papers, people say, yep, I developed this quantum algorithm, it beats my classical neural network. And when you read it in depth, you'll find out that people spent months optimizing the quantum model, and they use off-the-shelf classical neural network and didn't spend a minute trying to optimize it. Because if you spend as much time on classical models, you'll find out that your quantum models perhaps is not giving you advantage. Okay, so keep it in mind. It's always good to compare your quantum model against the classical one. Eventually, you're going to integrate your quantum solution with the rest of the organizational systems where it's going to play a role. And in some areas, it's going to be easier. For example, if you simulate chemical processes, molecular interactions, you'll find that you may not be able to easily replace quantum algorithm with classical one, or quite often you're going to combine both of them so that perhaps the classical algorithm will give you good initialization for the optimization that the quantum model could take on and improve further. Eventually, you're going to assess results, and maybe the loop closes. And so a lot of research needs to be continuously investigated, and new data arrives and being purified and so on. So that's a typical loop. It's not a specific loop for quantum model development, quantum algorithm development. So in here, we're going to talk about one specific type of algorithms, the algorithms which are to do with the estimation. Okay, in classical terms, people talk about regression style of models. Some people, like myself, I prefer to talk about estimation models. That means some machine learning models which predict continuous numerical outputs. Okay, so we don't try to attach a label which determines some category. We try to predict a value. It could be the price of an option. It could be the age of the customer. It could be the interest rate in this current economic climate. So what type of models we were talking about? Like definitely linear regression models, a whole lot of different ones, such as OLS regression, ridge lasso regression. We have nonlinear regression models, polynomial regression, support vector regression, Bayesian models, neural networks, variety of different neural networks, feed-forward and recurrent neural networks, time series forecasting models, some ensemble models, and many, many others. There's a lot of knowledge in classical machine learning in this space. Now, when it comes to quantum estimation models, the question is, when would you apply that model? Okay, so normally it's to do with issues of complexity, with high dimensionality of data, with the need for high precision and efficiency, where some classical models may lack. So usually the complexity of the situation is number one case, not necessarily volume of data. The applications are many, and so definitely in finance, healthcare, retail, autonomous vehicles, energy, whenever we deal with the problem of estimating a numerical value, such as risk assessment or drug effectiveness or demand forecasting or speed, power consumption or energy conservation and so on. And we're going to look at one particular quantum model that will be quantum neural networks. Both others, like quantum kernel methods, and they're very, very effective, and they very good at combining classical preparation of data and then quantum computation, quantum kernel computation. So we're going to start with the basics, and the basics are, this is very familiar for people who grew up with machine learning in their heads and or data science. How do you use your data to develop a model? So quite common, inexperienced people would have the data available to your disposal. It's a sample of data from population out there, and use a little or a lot of it. And then normal people quite commonly would use all the data for training and then use all the data for testing. And the problem with that is that the model would have seen the data throughout and used the data for learning. So it's not surprising that it will give good results if it's applied to the same data. Now that tells us nothing about how the model would perform out there with the new data from the population. So we need to basically split the data so that we could have some independent test performed to determine if the model trained on the data would apply to the data it had never seen before. And there's a variety of different ways of doing it. The simplest is what is called the holdout testing, in which case we use some data for training, then to optimize the model repeatedly in some iterations, we put some data aside for validation of results and learning how the model could be improved. And eventually, when we stop, we're satisfied with the model performance, we could apply it to the data that had never been used in this process of model improvement. So that's independent testing, or they call it honest testing. So that's one way of doing it. A much better way is use cross-validation of some kind of cross-validation, where perhaps the data is split into many segments called folds, and we repeatedly create the model out of, let's say we have 10 folds. We use 9 folds for training and then 1 fold for validation. We could even have another part of the data set aside for testing. And we can do it repeatedly, and then the performance could be judged as the average performance of all instances of that model trained on the number of folds less 1. So that's great, except that if you try to do it for quantum modeling, you'll find out that it could take you, on a simulator, it could take you hours or days to train one of the models. And if you try to repeat it 10 times, you're going to cry and you may not be able to afford it. As a lot of vendors are moving away from offering free time on the quantum machines. You need to pay for that. So it looks like the less thorough holdout testing. So the less thorough approach of holdout testing is still a good way of doing it. If your quantum machine is large, has a lot of qubits, perhaps you could run a lot of folds simultaneously and on the same run. Okay, so you could actually allocate your qubits to different instances of the model and then compute them in parallel. The problem is of the interaction and crosstalk between qubits could affect all of the computation. So that's actually an art form of running testing on large quantum machines. So what is the other problem? In quantum models, those quantum models are very sensitive to initialization. The very first parameter set that will prepare the weights before any testing starts. And depending on how you prepare that initial test, you may have very different outcome. So normally what you normally do is to either pre-initialize to have separate runs to identify a good initialization for the model, or have a number of different instances of the model, each initialized differently, randomly perhaps, and then taking the median model as the one for further training and further testing. So that actually multiplies the typical pool of models to be tested, because you also need to play with the hyperparameters of the optimizer, with different parameters of the ansatz, the number of layers, number of qubits, and so on. So the experimental settings for developing the quantum model could be very, very complex. Okay, so I'll talk about that. I'm going to use the simple approach here for holdout testing, maybe even give up on validation part and use training and testing as two partitions of the data, just for the purpose of this workshop. So how do we train a penny lane model? I mentioned before that a lot of complexity happens in Hilbert space. This is where the state of the circuit evolves, and a lot of things happen in the parameter space. This is where the optimizer actions upon the parameters of the parameterized quantum circuit. Okay, so definitely there must be interaction in the development between those two fields. So what's going to happen is that we need to have some kind of a circuit development. And usually what we do, unlike what I showed you in the very first stage, we create a so-called circuit factory. That means it's a function which will generate a circuit, and that function will have some meta parameters. The meta parameters could be held in the so-called closure. I'll show you that in practice. And then the circuit could be created for further processing. So the circuit will need to have some architecture, let's say quantum neural network of a specific number of parameters, maybe some qubits to be dedicated for input, or it could be more qubits to increase the parameter space. So there could be a structure, it could be maybe some of the parameters narrowing down, funneling to the measurement, whatever you could think of, and you could use other tools for building circuits like from PennyLane, or you could make custom circuit as required. So there's some kind of a circuit factory that will develop, that will create a circuit. A circuit in PennyLane is a function, as I showed you before, and you can look at it only as a side effect of the function execution. Function execution, which would take place assigned to some kind of a device on which the circuit needs to run. Okay, so that actually creates the circuit. And that circuit would have a number of aspects. The weight parameters, the trainable parameters that optimizer is looking at. There would be input parameters, which could take data, and the data gets embedded in the circuit. There will be measurements, the measurements which are eventually providing your data. And then you have gradients, and the gradients are attached to the parameters of the circuit, and the optimizer could navigate the gradient space to determine the best collection, the best optimal parameters in the cost landscape. Now we also have state evolution, which the circuit will evolve the state in the Hilbert space. Now, all of that most of it is invisible to the optimizer. The optimizer will see the weights because it tries to optimize the weights. The optimizer may see the gradients because the gradients are attached to the weights. The optimizer will see the input parameters because the data needs to be put in. The optimizer will see the measurements, the results of measurements, but will not see the whole complexity of what happens inside. The fact that the qubits are entangled, they have non-local interactions between qubits, between the parameters. All of that is invisible to the classical optimizer. It will not see the state evolution which happens in Hilbert space completely. Now, what the optimizer will know to do is it will have to use a cost function. The cost function, which will use a combination of the current weights in the circuit, and it will compare the results generated by the measurements against the results expected from the data. And the optimizer will take place in some kind of a training loop. And the training loop will start with some initial weights. And then within the training loop, we're going to have new sets of training weights attached to the weight parameters. The optimizer will be responsible for generating those parameters. And as a side effect, we may get some kind of a log so that we could see what was the progress of the training, whether it was improving or not improving, and so on. And typically, we would have some kind of a forward and backward movement when it comes to the use of the circuit, like in a classical neural network. So definitely we have some step forward to use existing current weights to perform the computation, generate the results from inputs, and then calculating the cost, the error generated from the entire training data set. And upon the analysis of the error, we could do the backward step to change the parameters. That's what the optimizer does. Keep it in mind, in Pendelane, everything is a function. It's quite different from what your experience could tell you. Eventually, what's going to happen is that we're going to measure the model performance. In training, we could catch perhaps the mean square error, which is used as an objective function to guide the optimizer. But you could also score it using some other performance functions like R-squared, for example. And so how can you do that? If you do it during the optimization stage, instead of days, you could be waiting weeks for the computation. So normally what's going to happen is that in this training loop, every time the optimizer prepares a new set of parameters and calculates the cost, we could capture the parameter sets and we could capture the cost for the further analysis. If we get those parameters could be later used to recreate the state of that circuit outside this optimization loop and score the model independently using other functions. Okay, so for example, we could fetch the parameter sets and we could apply R-squared coefficient of determination to see how the modeling was progressing according to this scoring method. Furthermore, we could apply the same model initialized with the parameters at this given point in the optimization process and apply it to the test data. And so we could later see whether or not the model was improving in respect to the data it had never seen before. As you can see in this example, it was performing very well in training and asymptotically well with test data, which is not happening very often like this beautifully. Now, what's important is to also analyze the errors. So in one of the exercises I'm going to show you, I'm going to ask you to create a residual chart in which you could see, depending on expected value, so expected value generated, by the circuit. How is the error distributed in relationship to the baseline? Okay, so whether the error was large, whether the error was coming from training data or the test data in reds, whether it was positive or negative. Maybe it's before training what happens, maybe after training. You can see the error from 0 to 100 in percentage, and after training, maybe to only 20%. That is good from the point of view of just visualizing the dispersion of error, but it's not actually helpful to determine how to fix it. A much better way of doing it would be perhaps to give the histogram of residuals or the errors to determine whether the distribution of errors is normal, and if not, what's happening in training and testing. So here we can see that in testing, we have some peak of errors, very significant errors, far from the mean. That only gives you the idea that errors do exist. And another way of visualizing errors would be to plot predicted value versus expected value in the truth according to data and then in prediction. Now, in this chart, actually what it tells us is, yep, the prediction and the truth, they align quite well, except for very high values where we have the highest discrepancy of prediction from what's expected. So in this case, we could work harder, or we could create a separate model which deals with high values of predictions. So if we talk about house prices, maybe houses above several millions of dollars, or commercial buildings, we need to build a separate model for those cases, in which case we could cut off all those errors, high errors, from the chart. So definitely we need to create diagnostic charts, and we could act on them to improve the model. Often with quantum models, the big question is the model still learning? And for that purpose, we rely quite often on those charts. So we could estimate the performance in training and testing, and we can see if the training is flattening out, that means the model is no longer learning. There's no more capacity for learning. And that could be good enough for many cases. However, there are other ways of determining the capacity of learning. You could actually calculate the model ability to learn before you start training. And one of those techniques is using the global effective dimension. It's the analysis and probabilistic measurement of the model complexity as a geometry in its parameter space. And usually global effective dimension is done by seeding the model with random parameter values to calculate its shape in a multidimensional Hilbert space. And you could also have a version of effective dimension measurements using local effective dimensions, in which you train the model, and during training you perform effective dimension calculations. It gives you a better view of what's happening during training. Does the model still have capacity to learn? And also, how efficient is each parameter in the model? Okay, so the parameter efficiency is important, and you could actually compare different ways of handling your modeling and compare different approaches to modeling. In this case, this is an example of from my paper. We looked at dealing with barren plateaus. Barren plateaus are flat areas of the cost landscape where there is nowhere, from the optimizer point of view, there is no way down the slope of the cost landscape to find the optimum. It's the flat area. I'll talk about it in a second. So we investigated 4 different ways of dealing with barren plateaus, and then we used local effective dimension to determine which of those approaches is actually impacting the model's ability to learn. So, yep, we used mitigation strategy for barren plateaus, but that mitigation strategy had a negative impact on the learning of the model itself. So that was actually we tried to figure out, is the model still learning, and if so, what is the efficiency of its parameters? It's also a good idea to compare your quantum model to classical models, and for simple cases, this is brutally honest result. You find that beating classical models is tough, is difficult, and if you spend some time on tuning your classical model and then tuning your quantum model, they go head to head in a race for efficiency. That was actually example how we were using variety of different architectures and different structures of a particular model, and look at the model performance across the training and validation using variety of different scoring techniques, just to determine if the Pendelane PyTorch model was comparable to the classical model. In this particular case, it was head to head. Pretty much we could not get significant advantage over the classical model. So what it tells us is that you can't be too cocky about that. You need to have multiple models run, multiple instances of the same model to get the average performance. You need to actually score it using a variety of different techniques to determine what the performance really looks like. And I mentioned barren plateaus. And barren plateaus happen. It's a great. There's a lot of papers written about barren plateaus. I showed you initially that cost landscape. It was a nice valley, the nice valley which was created for the simple neural network with 2 parameters, classical neural network. And you would imagine when you have a lot more parameters, the model is going to get richer. It could learn more complex data. And so it does. The problem is that with the number of parameters, we create more and more independent dimensions in the model. And there is a simple geometry problem here, that with higher dimensionality, the cost landscape flattens. And it's nothing to do with the modeling. It's nothing to do with quantum effect. It's nothing to do with interconnections and geometry of your modeling. It's just plain geometry. Okay, what does it mean? Why I'm talking about it? Imagine we have a ball. A ball which is a 2-dimensional is a circle, 3-dimensional is a sphere, 4-dimensional is more complex to imagine. It's maybe a sphere moving in time. And of course, it could be 45-dimensional and higher. If you start calculating the volume and the surface of multidimensional ball, you'll find that the highest volume of the ball is at 5 dimensions. This is weird, but this is actually mathematics. And after 5 dimensions, the volume of the ball starts shrinking. So the ball still has the same radius, 1 in all dimensions, and the volume starts shrinking. And the surface, it starts growing. So what happens is in the higher dimensional ball, most of the volume concentrates close to the surface. And I imagine that here only that it's empty. It's not empty, it's just full, but there's no volume. The volume shrinking, the surface is growing. What does it mean? It means that if your cost landscape is plotted within that multidimensional ball, because if your model has, let's say, 4 parameters, it's a 4-dimensional ball. Your cost landscape is plotted, and the height, the elevation point is the distance from the middle of that ball. So it's got a shape. It's got some valley, and the valley is closest to the center, and they have some points far away from the center. If you find some random initial point, the optimizer is going to find a way down to the optimum. It's easy to find it. What's going to happen if you have a high dimensional ball where all the volume concentrates near the surface of the ball? It means that the cost landscape needs to fit in that surface. It's getting thinner and thinner. There's less space to represent the elevation, which is the error. And so if you pick a random point on this surface, the optimizer could look around and it's flat and flat in all directions. It's very difficult to find the optimum point unless you are standing just very close to it. So that's what happens with barren plateaus. The more parameters the model has, the flatter is the cost landscape. What can you do about it? You simplify your model, use fewer dimensions. You could use a different measurement of error. So instead of using Euclidean error measurement, you could use some other hyperbolic measurement. You could try to initialize your model better so that it's not a random point on that landscape, but somewhere close. How can you do it? You could also develop your model stage by stage, each time optimizing only a fragment of it, perhaps only to determine how close you could get to the optimum, and then you're very close to the valley down. So there's lots of different ways, and it's a curse of dimensionality. Barren plateau is a purely geometry problem. What happens with quantum models is that we face the quantum noise, and the quantum noise could be higher than the indentation in the flat area. So the optimizer could look all around and could only see the bumps of noise on the surface and cannot see anything beyond the noise. If you have higher differences in the elevation, the noise could be absorbed into the surface, but not in this case. So that's what barren plateau is. The lesson of that is use fewer qubits, fewer layers, fewer parameters, use local cost function, do not measure all qubits. The reason for that is that the measurement outcomes get sparse, it's harder to interpret. Use non-Euclidean metrics, beware of parameter initialization, and use some barren plateau resistant models, such as quantum convolutional neural networks, where the models learn using a small convolutional filter, which is low dimensionality, and the optimization is not across the whole geometry, multidimensional geometry of the data. Okay, what can you do about quantum estimation? We have problems. For example, in variational quantum algorithm, it's very quick to compute forward execution of the circuit, very slow to work backwards to calculate the weights, and there's possible solutions for that. The number of shots that need to execute on a quantum machine, that actually could determine the precision of your results. So the more shots you have, the longer is your training or the evaluation. The less shots, it's quicker, but it's imprecise results. And you could actually move into like analog quantum computing. You could rely on continuous variable quantum computing like photonics. And there's other ways of dealing with that. But if you rely on gate-based quantum machines, you need to suffer that. Quantum noise, and of course, that affects the training because of the barren plateaus. It affects also the precision of results. So train models with simulated noise to determine what's going to happen on a real quantum machine if you use the simulator, and apply error correcting and error mitigation techniques, which we were not going to talk about it in this workshop. Now we're going to look at some demos, and I'm going to use some synthetic data, and you're welcome to use some other data to play with it. And I'm going to walk you slower than before so that we have more time spent on understanding what's going to happen. Okay, so that will keep your attention on the simplicity while I attacked you with complexity in the first session. So let's look at the demo. Any questions so far? Let me just look at, I may have had questions. My chat disappeared. Okay, so I think that most of the questions would have been answered. Baryon plateaus are exactly the same problem as vanishing gradient problem in machine learning. Yes, thanks, Alexandru. It's caused exactly by the same geometry problem. Okay. What the volume refers to in the n ball, it's the volume which is n-dimensionally calculation of its space. So the volume of the circuit is calculated differently than the volume of the sphere, and of course the calculation you add an extra dimension which needs to be added to the calculation. It's a standard formula for the calculation of n balls. Okay. If QML is not able to beat classical machine learning, what is the need of using QML? Well, it's not able to beat classical machine learning. You need to have a problem where the QML is beating the classical machine learning, and there are such problems. Okay, so basically, a lot of work is done in quantum machine learning, not for the purpose of beating the classical technique, but to understand how quantum machine learning algorithm could actually work. So, the same thing with machine learning. There's a lot of statistical techniques which are much better than machine learning techniques. Okay, so they give you, machine learning, classical machine learning has a statistics to fight, like regression, a standard linear regression versus linear machine learning techniques. And of course, by now we have algorithms in machine learning which give you superb results. A good result is all the AI. So in machine learning, quantum machine learning, we're still learning how to create those algorithms which could work. Now, the question is whether variational quantum algorithms, which mix and match classical and quantum techniques, are the best way of doing it. It will be much better to do it all in a purely quantum ways, but it's very, very difficult. And that creates very large circuits, and we don't have reliable quantum circuits to do that yet, but it's coming. Okay. All right, so coming back to I did show you some very, very simple quantum models, and I'd like to move into something which actually makes sense. Okay, so this is a very simple quantum estimator in which we're going to create a regression like data set. And we try to improve a simple quantum model by changing its properties, changing entangling methods, the number of qubits or wires, the number of training epochs, changing the optimizer. So we're going to play with that model, trying to get it better. And in the process, we're going to learn what actually makes a difference. Okay, and I'll also show you how to structure your data. Okay. So this is just to find my utility functions. I'm going to use pandas to read the data in, use time and some math and operating systems, and matplotlib to plot things, import all the utilities, especially utilities for drawing the circuit. And important thing is we import PenDeLane and we import the NumPy from PenDeLane. If you don't do it, you may have some issues with compatibility between PenDeLane and some mathematical calculations. The main one is that the NumPy arrays in PenDeLane become tensors. That's what you want because you want the tensors to have actually ability to assign gradients. And I'm going to show you that we can use the standard scoring functions like sklearn, R-score, and mean square error, but not during training, but after training for scoring purposes. The data set I'm going to use is the data set, synthetic data set to make regression. So I'm going to import the data, and the data looks like this. So it's three-dimensional data. We have only two features, feature X and Y, and the target value is the Z-axis. So that's what our data looks like. You can see there's a slight noise in the surface, but it should be very simple for classical model to fit the data. Close the sidebar. Yep. Better? Okay, sorry about that. Thank you for reminding me. So we're going to develop the model. Can I make the model bigger? I could shrink it. But then you won't be able to see the text. Let's okay. Is the text visible? Okay, so we're going to develop the model. Again, I put some constants up front. The first simple thing is I'm going to create a model of specific number of qubits or wires, or in this case is features. I'm going to have two features only in this data set. So we could say 2 is number of features. The number of qubits could be larger. So we could actually have extra qubits, but the input to this particular circuit will be on 2 wires. We're going to use a number of layers. And what we're going to do is to determine how we're going to represent our weights. So we could represent the weights as a single rotation, or we could represent the weights as rotation in X, Y, and Z coordinates. So 3 values. So for that, I'm going to use standard PenDeLane structures, and there's only 2, and I'm going to show you that. In the previous modeling, in here, you can see that I'm using here specifically just a single value to rotate, a single value. So this is for the data input, but I'm using so-called strongly entangling layers, which means that I use 3 rotations per parameter unit. So that means it's a more weights available in the circuit. Or you could use a simple entangling layers, which means a single value. And I'm going to play that in this case. What else is here? I'm going to define, in this case, I'm going to create wires. I'm going to create qubits, predefine them. It's a list of number of qubits. And we have training hyperparameters like number of epochs, number of shots. Now, I said I will not be repeating the measurements. I will rely on the fact that I'm using the simulation, which will determine the statistical distribution using just calculation of the statistical measurements. So no shots will be required. I will allow the model to create and emulate the number of shots statistically. This means the simulation is much, much faster. I also have here some additional information about in what range of angles I want to encode the data. So I could assume that I will have the data from 0 to pi, which is on the right-hand side of the block sphere. And perhaps I will have some margin so that if there is a rotation to the left and right, it just jumps over to negative values. I may prevent that by increasing the margins. But this will get changed anyway during the training because the rotations will go on to change the values everywhere. So perhaps margin 0 would be good enough. But let's have this optional. Okay, so I'm going to preprocess the data using standard scikit-learn preprocessing. So I'm going to scale the data to fit my representation for qubits. I didn't, sorry, maybe I talk too much and I don't execute every single statement. So I'll do it from scratch. Okay, I talked about sklearn, but then I never executed it. Okay, so I went through this. So I got min-max scalar. It's a standard technique for machine learning, preparing the data. And now I do the split to have my training data set and test data set. And I'm using 62 values for, sorry, 67, 60 test. Oh, 67 values for training and 33 values for testing. And now when I have all those partitions, I need to make them tensors. And at the moment, this is just the training data, the input and output. So there's no gradient required. This is just plain data flowing through the model. Okay, now it's worth to explain what it is. This is how I'm going to calculate mean square error, the cost function, given the targets and predictions. So I have two vectors with the values which I expected and the values which were predicted. And all I do is simply to calculate the difference between each pair of values, square it, add it to the cost, divided by number of items. It's a mean square error. This is the cost function. However, that cost function that cost must be generated by applying the model to inputs and comparing with targets. So this is what is done in in a functional way. So I create my the cost function factory, which is past the model and the cost function, this function we passed in. That model will have to be used repeatedly to apply that cost function to each data pair. So that model is going to be remembered and be available to the function defined internally but returned to further computation. So it still remembers the context of its creation. So I create a dummy function inside, which takes parameters, inputs, and targets. But when this function is created, it will know as a non-local context the model and the cost function from above. So it means that when given parameters, inputs, and targets, I could apply the model to the parameters and one of the many inputs to create a single prediction. I do it for the whole list. I get all predictions, and then I could compare targets to predictions. And this is suddenly available as a full cost of applying the model to the data. Okay, makes sense. Those of you who have never done this in Python, it's hard to grasp, but that's how we do it in Pendelane and those functional languages. If you learn Lisp, you know how to do it. Okay, so I think that in your version, we're using default qubit by default. I want it to run fast. I use Lightning Qubit. If you get into trouble, default qubit is a definitely safer way of doing it. So I'm going to use the Lightning Qubit, which is the C++ written qubit device. Okay, I'm going to develop a linear model in exactly the same way I've done with the cost function. So I'm going to create a factory function called QLinear, which takes number of wires, some scalar, and the information whether they want to have a strongly entangled layers or basic entangling layers. That means basic entangling layers, it uses specific one operation for one rotation, whereas strongly entangling layers use 3 operations. There'd be y, z, and y again. You could think it's x, y, z, but those two will generate all directional movement. So this is the interesting part. This is the context, the n wires and scalars, which will be available to this function as non-locals, even though that function finished operation. So it's very simple. We create wires, local wires, qubits. A scale input if so required. By default, scaling is 1. I add angle embedding layer, which is the standard encoding block, which will create as many layers as there is wires. And the inputs will be sufficient for that. We need to provide sufficient number of inputs to populate angle encoding for each qubit. And then depending on whether I want the basic for truth or non-basic entangling layer, I will add that layer or the other layer. And expectation values, projective measurement on z-axis is what's going to be attached to a single wire or qubit 0. Okay? That is done. And what I'll do, in the previous case, I had model development independent of dealing with what type of initialization I need to do. So I would have to either initialize parameters using one line or initialize parameter or using the other one. So here what I do, I integrate it into a separate function so that I don't need to worry about which entangling type I'm going to do. I'll have a function which will calculate the shape. And in fact, there are standard Pendelane shape calculations function depending on those basic and strongly entangling layers. Okay, so now I'm going to create a model which has so many wires and has a basic entangling. And then before, what I did was to create a decorator which automatically turned the function into a node. Here I show you how to do it step by step using instructions. So I could create a function. That's actually created a function. It's still a function which was generated by QLinear function. Now that function could be passed to the Q node, and you could attach device. And you could specify the differential method. So there's different ways of calculating gradients. And this is adjoint. It fits my qubit type. So qubit pi was lightning. And each device will have different ways of doing differentials. Okay, so differential method is adjoint, which is suitable for my particular qubit. And the shape is determined by the shape function based on the same parameters which were used for creating the model, so I can't go wrong. Okay, so now I need to create the parameters for testing so I could actually plot it and see my particular circuit. So I know some input, I have some testing parameters, and this is what it looks like. I specify number of layers. We have 2 inputs, and then 1, 2, 3, 4, 5 layers and a single measurement. Okay, so we could actually apply that model to the data and see the results instantly. So this is for the test parameters and for test data. But that model hasn't been optimized. So I want to optimize it, make it better. Okay, it's started with some random parameters. So how do we do it? So we're going to create and train that linear model. I start with some random seed so that you could repeat it and you get the same results. I pick the ADAM adaptive momentum optimizer with some step. I generate my cost function. So this is the function written for that model. So that model will be remembered for the cost. That cost function remembers that this is the model I'm going to apply. And this particular mean square error cost function will be applied in the calculation of cost. The parameters are of a particular shape. So I did the shape calculation here. If you wanted to know what is the shape, I'll show you. Because it's always think, what the hell is shape? This shape says 5 layers of 2 parameters each. If I used non-basic entanglement, it will be each operator will have 3 values, and it will be 3 values in the shape. We'll see that in a moment. So this is actually not a flat vector, the parameters. The parameter is structured. That's very different from Qiskit, in which you pass the flat vector and it gets allocated appropriately. Okay, so the training loop is like this. We are going to collect the calculated cost, and at each stage, at each iteration of optimization, we're going to collect the parameters so that we could actually later on calculate a different scoring for each model and perhaps apply it to test data as well in the process. I'm going to log the results maybe every 10th of the epochs. So what happens here? This is the same. It's a step and cost function, which takes the cost function, which takes a single argument, a single parameter, the same parameter, but it varies that for each x and y pair. The step and cost function, it performs the following. It takes the step forward. That means it calculates from input, calculates the output, calculates the cost. The cost is being determined by the optimizer analyzed, and the step backwards updates the parameters which get generated to be used at the next iteration. We collect the cost because the cost is returned as a tensor. So we want to get the value out of the tensor. We append it to the list, and the parameters get appended to the list as well. And we perform it, and then we get some statistics. Hey, I stepped over this summary. I talk and I don't calculate. Okay, so now, okay, so definitely it improved. So the cost started at 0.5 and then it was getting better, better, and got stable very quickly. And so I could calculate the optimal scores. So now I apply that model. I could find which model was the best. So which model was the best? So we need to find the best model. And I think that it's somewhere here. It actually finds the model, which is we find the minimum of during iterations, and we get the minimum point in a cost, and then we could fetch that particular parameter set for that model. Okay, so here we're going to use that model and apply that model to new data, or apply that model to different scoring. So here I'm going to calculate R squared and find the maximum R squared and find where it occurred. So I do it in iteration. I have so many parameters. So we have a history of all the parameters. So all the parameters have been saved at each step. So I get the next parameter. For that particular parameter, I'm going to create a model which uses that parameter set and uses the training data. So I get the result. And so those are the predictions for every single x value. Now here I can use the standard R squared scoring function, which is from scikit-learn. And because I'm not training the model, I don't need to rely on gradients. So I could simply calculate the values. So that I'm allowed here. I wasn't allowed to use it in this stage when we were stepping and cost, where every single parameter needs to be differentiable. So the gradients need to be calculated. Here I simply calculate the values. And then again, I could append the R squared and I collect it in the process. Okay, so I have some R squared values. And here, your homework will be to calculate your testing mean square error and R squared. I think we'll go through that. Maybe I'll leave it for you. But you can see that we improve. So we could record that the best R squared was 0.67. Not great. We would like R squared to be close to 1. Now, whether mean square error is good or not, we don't know because it all depends on the range of values that we were calculating. So this score is unit free. That score depends on the range of values. And in our case, this is to do with data encoding scheme. Okay, so we want to minimize this value, maximize this value for testing. So sorry, this is for training data, but we want to maximize it for testing. The first few steps in this particular exercise is to improve the training outcome. Okay, so the first thing we're going to do is try to see what happens if we change entanglement, type of the entanglement from basic to more complex. So have more parameters per shot. So here is in this particular case is a very simple operation because I have anticipated this. And I simply say, let's use more complex entanglement process. And you're going to step it through all of this. And we're going to see that suddenly I get RZ, RY, RZ instead of a single operation. So clearly it's a different approach. So This comes from the fact that I'm using strongly entangling layers as opposed to basic entangling layers. And so the shape of all the weight of the weights, the trainable parameters is different. So the 5 layers of 2 qubits, 3 parameters per layer. Okay, so this is the shape of my weights. So if I were to create the initial weights, they need to be shaped that way. Why is it important? It's important because when we know the shape of the weights, the smart classic optimizer in a simulator could actually take advantage of it because it will know which of the weights are earlier, which of the weights are later in the process. And so it could do backpropagation on this. Otherwise, it cannot be done because if we simply use all those weights, it's a big blob of trainable parameters. We don't know the precedence of those parameters. The backpropagation cannot be done because we don't know which are the earlier, which are the later parameters. Okay, so that's useful. And when we do the hybrid models, that's even more important because we're going to interface the classical component with quantum components, and they will be optimized together. And there is actually specific mapping between torch and PennyLane, so that the torch optimizers could take sort of like a view inside. It's not actually inside the model executing, but it's the view inside the template which describes the parameter structure. Okay, so in this case, we're going to train the loop. Here we had the best cost was 0.02. Now we did a one small change. And let's see if it has any impact on the outcome. You can see that instantly we have better result, but maybe not as good as it could be. So the question is, what else can we do? Can we increase the number of qubits? We can't because we have only 2 features. We would have to create a very different structure of the model, but we could easily increase or decrease the number of layers. So let's see what happens if we increase the number of layers. Let's make it 8, perhaps. This is going to be much more complex structure. Now, I assume that with a more complex structure, I may need to have maybe more epochs. So let's increase the number of epochs because the model will be learning slower. Okay. You can see it's many more parameters. That means the learning will be slower. The shape is 8 layers of 2 qubits, 3 parameters each. And then let's see. You see, there is a bit of delay. So lucky I'm using the Lightning qubit rather than default qubit. Default qubit will be much, much slower. So before we had 50, at 50, you can see it's not, wasn't doing very well. So it's good to actually increase number of cycles. I think, I can't remember what it was a moment ago, but probably if we gave more epochs, maybe it would be an improvement. I wonder what happens if we reduce number of layers. Would the simpler model be better? By the way, we could do the scoring here. Scoring, the first scoring was R squared was 67%. I can see that R squared is definitely better. It's getting 93. It's perhaps is overtrained. So it's reaching the peak. If we plotted it, we can see there would be um, the peak somewhere in the middle, and then the model gets overtrained and it's getting worse. Okay, so, or maybe there's some oscillation there. Who knows? Um, one of the tasks here is to calculate the testing mean square and R squared, and then plot. This is a ready-made function for you, and we could actually plot the result. Um, I have actually done some of those things, and I'll show you what the last version, box. Can't remember what I've done here. Let me just run it. Just see if we get plots. No, not yet. I'll just close it. I think that was all best. A change in coding, residuals, test scores. Okay. So here I was experimenting. I was changing the this which aspects. I found number of layers, increasing it was not actually effective. The more complex entangling layers was effective. Number of wires was 2. Number of epochs had to be increased. And what else was done here? I was playing with initialization and playing with the range of values. So I increased the margin from 0.1 to 0.5, so it has more narrow. So the variation between weights at initialization was smaller. I was playing with different optimizers. So I tried Nesterov Momentum Optimizer, but it wasn't really an improvement. So let's see how it works. And now I have the code for applying the weights to, which is the model at each iteration of the optimization. Okay, so this is actually, it's still training. You can see that there was a lot of steps, a lot of experimentation, and I did improve it by from 0.3 to 0.007 or 8. And this is the calculation for training R squared. We get 98%. And this is for testing. So this is the vital part. You can see that the code for calculating scoring the test data is almost identical to scoring the training data, because we simply, instead of using the training parameters and training predictions, we use testing values to calculate testing predictions. Apart from that, it's exactly the same structure. And I get pretty good results on tests. So this is the result for the training. You can see that both lines are hugging each other. That's pretty good. And this is for the R squared is approaching 1. So it's a very good result for this data. But this data was actually very, very simple. But when you think about it, so even though it looks complex, but this is actually a very simple linear fit. Okay, so this is almost linear. So I wouldn't expect anything else. However, when you deal with this, you can actually go and do something more complex. So this is actually from the same source. You get a different data set. It's called the max withdrawal. The data is more complex. Okay, so we have the color. It actually gives you the value you need to predict. And it's got a very strange shape. It's definitely not linear as it was. To use this data, it will require a bit of creativity. It still uses feature X, feature Y, and the color is the third value. And I think that feature Z is, so the color is, I think, what we need to predict. We need to check it. Okay, so that would be a challenge for you. Can you actually use this data set? You'll need to have 3 qubits for that, and recreate that to fit it properly. Now, what you can see here is that I write my observations at each task I'm running. So I'm just recording. I said what I've done. Sometimes I write in what cell I did the change, on what line, what was the results I obtained in training, and once the testing appeared, I also specify what are the testing results. Okay, so those of you who work in the lab, you know what I'm doing here. You really don't want to repeat your work more than once. And ideally, those results should be logged automatically into a database for further analysis. So here I show you manually how to enter it. Like a good lab assistant would have a lab book and write everything in it. But the data should be, the results and the data which created the results ideally should be stored in some experimental database. So we could always recreate it and we can always report it in a more fancy way than this. So normally what would you do is all the data creation could be a separate Python program. Then the model training, a separate program you could run in batch because you could run multiple times. If it's complex, maybe the model training, the parameters should be saved every so often. So if it takes a week to train, you could recover halfway through and you could take from the midpoint and start training further. And then the beautiful charting and plotting could be done in a notebook for easy reporting. Okay, so that would be the normal path for developing a program. But most of you, especially if you're a scientist, that's exactly what you do. Okay, so the question is, how do you run it on a quantum computer? If you use PennyLane, and PennyLane has different backends. And there's around 50 of different backends. So you could run it, default qubit, lightning, Qiskit remote. So you could actually, if you have a Qiskit account, you could actually deploy your PennyLane program on a Qiskit machine, on a real quantum machine. Or you could actually run it on the local machine. So there would be the Xanadu machine, also on Bracket, on AQT. There's a lot of different backends. You could use Cirq simulator. Another Qiskit IonQ machine. A Rigetti machine. So there's a lot of choice. So it is a truly open source product, and it can fit to many different machines. But originally, it was written with an idea that it will be executing on photonic machines, which have a very different way of operating. Okay, if you are into photonic machines, Xanadu released another product. It's called Strawberry Fields. So Pendelane, Strawberry Fields, they got into Beatles probably. The Strawberry Fields is similar to Pendelane, except that it's got gates specific for photonic machines. So you have splitters and mirrors and things like that. And so you could actually build a slightly different circuit, which is optimized for running on Xanadu machines. Okay, so that's what we do. So what happens here? We could actually run one more test. I want to show you what residuals would look like. So eventually I ran it and I had a really good results. And I wanted to plot distribution of errors. So this is my simple residual plot. And if you plot it before training, it will be 100% errors. That's reduced to majority of errors within 10%. It's still not that good, but we know it's 10% from the R squared. We could actually calculate back the distribution of errors. And it's a great way of starting because the data it allows you, the structure of this notebook allows you to play with different parameters of the data of the model. Okay, so that is actually what we planned for today. I wonder if would you like me to explain more about this or explain the challenges for the previous session? I'll show you the challenge here. So here in the previous session, hopefully by now, if you walk through the creation of those models, it will be simpler. The main problem will be with dataset 2. That's a real challenge because it seems no matter what you do, how you play with the model, you're not going to get a good fit. So the question is to identify the problem, and I can give you the hint. The problem is not in the structure of the circuit. That's a hint. The problem is elsewhere, and you need to find out where. Okay, so that's actually an interesting problem, but you could try. You could try. You could approach it. You could get it almost right, but it will never get right. So that's actually the tough problem. Then there is a challenge task for those who push further, who would like to write the on optimizer. And those of you who know Torch already, I recommend this. So you could actually write a class. This is actually the RCD optimizer. You could write your own optimizer and then start using it. So you can see that it's a step and cost function that needs to be required. A stepping function needs to be done in it. This is actually an optimizer which optimizes a single parameter at a time. It's excruciating slow, but you could write a fancy optimizer, maybe some kind of a particle swarm optimizer. Let's see. So that's actually a challenge for people who are very good with Torch, and they're good with Python classes. So you need to read a little bit about optimization. It's a link to Pendelane, how to create your own optimizer. But tomorrow I'm going to show you how we could use PyTorch and start creating hybrid models. And so it means that we have access to Torch vast repository of optimization techniques. And it's actually interesting how to marry them with quantum models. The next difficulty here is actually not a difficulty, it's just to get your hands dirty. We answered the question why a single qubit was good for that data, because the data was sinusoidal, and what a single gate does is to create a sine function automatically. So whatever sine function or whatever combination of sine, cosines, and you're going to make, it's very easy to reproduce it with simple rotational gates. So basically what those models do, they implement Fourier transforms. Okay, so that's the simple thing. Even a single qubit, it implements a Fourier transform. It has limits. I found that a single qubit could give you some fantastic results on simple functions, but not very good results on chaotic data. So if you use like Mackey-Glass chaotic data, then you'll find that you need to have more complex answers, more complex model structure. But in here, you can actually play with those parameters and experiment. Now, the question is here, I'm going to show you one problem with the very first, with data tool. Okay, that was session 1. I want to use the re-uploading answers. What does it mean? So this is the first model, the simple model. This is the second model in which the data is propagated across different qubits. And here the data is propagated across qubits and across layers. And let's see what it looks like. Okay. So this is the same value encoded as a rotation y. And you can see the same value is distributed at each qubit. So each qubit and each layer. That looks like a lot of waste. Why not just in one spot? That's because if you look at the mathematical recursive formulation of Fourier transform, the Fourier transform written recursively is basically what you see here. Okay, maybe we have fancy and interrelationships, but the Fourier transform, the rotation of that value on one qubit or all qubits, then we have the same rotation applied to the rotation, but it's slightly transformed. Then another way. So this is actually, you can see that if this is value of x is getting x squared, x to cube, x to fourth power. That's what re-uploading of data does. It actually creates higher order terms in this structure. So if this was a function that creates higher order terms by re-uploading the data. And it's actually fascinating how effective it is. I'm just going to run it. And I'm going to give you a comment on the problems with this particular circuit. It's much slower now. I can't remember how many epochs I have, but it's maybe 100. So this is 15 seconds per 10. Let's wait. Okay, the problem here is I use the Lightning qubit. Sorry, I use default qubit at the moment. But if I use Lightning qubit and I use then adjoint. So what's adjoint? Adjoint, it reverses the order of all gates. So if you have a gates sequence, if you take the adjoint of this circuit, if the circuit where every single operation is done in reverse order. In Qiskit, there was something called invert the circuit. So what happens if you use reversal of the circuit? You could actually get the gradient calculated between those two using sort of those two components, the mirror images of each other. So basically, you need to create the inverse of that circuit. Unfortunately, what I found is that Pendelane cannot cope when you have re-uploading applied. You have interleaved parameters and data. And it actually, when you do adjoint, it shoves all of the data to the front and all of the parameter weights to the end. And so it actually gives you error later on. So I actually posted it to Pendelane and I hope to get the answer. However, so definitely we have problems applying Lightning Qubit to this particular case when you have interleaved parameters with weights. However, later on when we do more complex hybrid methods, what I discovered is that default qubit, when it's applied to one specific differential method, which is called what's called the gradient descent. So it's actually, oh, I forget now what it's called. I have to check. I have to check what it is. Basically, it's a method which is gradient descent method. And it actually works incredibly fast. Okay, so I'll tell you what it is because I was using it yesterday. Maybe I was using it somewhere here in the very last challenge, or maybe not this. Okay. Let's look at the results of what I calculated here. So we get some really good result with more complexity to the model. And we have a perfect fit of this unusual data, which I'm not telling how I've done it because you can figure it out yourself. But the most important thing here I wanted to show is that I used re-uploading of the data. I use parameter shift with default qubit because it will not work with Lightning Qubit. So that re-uploading really improved the final result. If I did some magic trick to work with this data, which you need to discover. So that's the homework for session 1. For session 2 is to use Swiss roll. And this is probably harder than a Swiss roll, but the other one's more fun to work with. And please do put your comments because later on when you do the quiz, you want to refer to your fantastic insights. And so the certificate will, you'll be able to, once you get so many questions answered on the quiz, that will determine if you get a certificate for the course or not. Okay, but Pavel can answer more questions about certificates. Can re-uploading be done with different other encoding schemes? Yes. So Tomasz actually answers all of them. Thank you, Tomasz. That's right. So amplitude embedding is tough. They usually do it at the very start of the circuit. Okay, so thank you so much. Any questions, please do ask. You may want to put your hands up and you're welcome to questions. One more thing is you have those early notebooks which are asked to do yourself. So there's a tiny model which we walked through. The other one is measurement tests. So that just shows you how you could measure different results and how you interpret it. Okay, so it's worth walking through that. Which we haven't done. So we have here amplitude embedding and encoding. We have here basis embedding. We have measuring expectations. By the way, in PennyLane, we have a great variety of different measurements that you could apply. They are just part of the library. In Qiskit, for example, to do expectation value, you would have to actually write your own code or the circuit for that. So here it's all done as part of a simulator. It's great. We could measure this entire state of the circuit. Okay, so the state of the entire circuit, and you could interpret it. You could analyze the amplitudes and expectation values, as you can see here. So that's actually very, very flexible. It makes PennyLane my favorite software for quantum computing.